All right, we've covered most of the applications in chapter 2, and I want to talk about one or two more later, but they're quite a bit different, and I want to do them when we're face to face. So, for these videos for the rest of this week, I'm going to jump up to chapter 3. And chapter 3 is all about finding antiderivatives. Okay, certainly the fundamental theorem requires us to know an antiderivative. And later on, we're going to look at other problems, certain applications that require not a definite integral like we've been focused on, but actually just the function part, the antiderivative. And as you've heard me say before, most of you, finding antiderivatives is more difficult, more challenging than finding derivatives. For derivatives, there are some facts we need to know, and then there are rules that just tell us what to do, and we follow the appropriate rule. The product rule for products, the quotient rule for compositions, the quotient rule for quotients, the chain rule for compositions, and so on. Not a lot of creativity, a lot of care to detail is needed, but not a lot of creativity. For antiderivatives, it's quite a bit different. And so I've started off here with just a review of what we already know. And the first thing we did was we talked about the basics. They just take every derivative fact, you can turn it around and make an antiderivative statement out of it. And we've been doing that. And I hope we're pretty good at it. We have kind of a list that I hope you have memorized. Okay, and then we took it one step further. We were able to take a close look at the chain rule and for derivatives and figure out how to get antiderivatives out of that. We ended up calling the technique by substitution, integration by substitution. And then we actually showed, maybe you remember, I think there was a problem on our final exam where we can actually do more than just reverse the chain rule. That is, we could utilize the substitution. If you don't remember, that's okay. Maybe we'll get a chance to talk about it again one of these days. But that's where we stand right now. And there are still huge gaps. In a recent homework assignment, we needed to know, if we're going to use the fundamental theorem, we needed to know the antiderivative of x sine x. And we don't know that. Okay, I think another problem in the homework required us to know the antiderivative of the square root of 1 plus x squared. Maybe we needed a substitution and then we would get here. And we don't know that antiderivative either. We haven't seen a function whose derivative is x sine x or the square root of 1 plus x squared. And therefore, we don't know an antiderivative. And using the substitution, there's just no way to figure out what's going on here. So, we're decent at integration. We know a lot of things about it. We've spent a lot of time and effort, but we have more work to do. And, you've heard me say before, I think finding antiderivatives is more fun. I mean, it's a challenge. And we have to be creative. We have to have an open mind. We have to be willing to try some things. And with all that said, in chapter 3, we're going to learn some techniques, and those techniques will just tell us exactly what to do. I'm going to justify the techniques. I'm going to show you why they work, and then we're going to practice using them. And, that's kind of a pattern we followed. We justify what we're doing, why we're doing it, and then we solve problems. And when you're solving the problems, you don't really need to know why we do it this way. You just really need to focus on how. So the same thing here. I'm going to show you why the biparts technique works, and then we'll just practice it over and over. Of course, if we want to get good at it, we're going to practice it a lot. So let me create a little space here. And we're going to start with the chain rule. For derivatives, I'm going to write it briefly. So let's say we have f times g. We take its derivative, and we all know you get f g prime plus f prime g. Okay, let's write that. That is, this is a function, the left-hand side, and this is a function. Because those functions are equal, they have the same antiderivatives, except for perhaps a constant, which disappears. in the derivative process. So if I think this equation here comes from the product rule, let's just integrate both sides. That is, find the antiderivative. And so the left-hand side, because it's already a derivative, if I integrate it, the antiderivative is just the product, FG. It undoes the derivative. And on the right-hand side, we get the antiderivative of a sum. I'll write d as if x is the variable. And we know the antiderivative of a sum is the sum of the antiderivatives. So I can break up across this plus sign into two separate antiderivatives. Okay, and now our hope is that one of these guys is known. Let's say it's this one. And then I can solve for the other one by subtracting this across. So the integral, and now I'm going to write all the details out, f of x, g primed of x dx is equal to the product. We're subtracting this guy over. The fg is already there. F of x gx minus the integral of f primed of x g of x. And if we assume, as we are, that we know this guy, then we know the antiderivative. It's just the product, f times g, minus this known function back here. So that's the hope. This guy is unknown. He's the guy we're hunting for. And then we hope that we can figure out this integral. And if we can, then we have the unknown one. Okay, so maybe an example would illustrate how this goes. Okay, so here's the antiderivative you ran into in a previous section. We didn't know its antiderivative. And now we can use by parts to figure out what it is. Notice I've written the structure of by parts over here. And the trick is to, or the method I should say, is to take the function that we have that we need the antiderivative for along with its differential and split it into these parts here. F of x, g primed of x, and the dx. And in order to make it work, whatever we assign to f, we have to be able to get its derivative, because notice on the left-hand side is just f. On the right-hand side, on the integral that we're hoping, we will know we need its derivative. Okay, and the portion of this original integral that we assign to g prime, we'll assign it to g prime and the differential. Then notice on the right-hand side, g only shows up without the prime. So to go from g prime to g, we need to integrate. So we need a function whose antiderivative we know. Okay, so I'll illustrate for this example, and I won't talk too much about strategy. I'll just show you how to do it. And then we're going to take another look at this particular relationship. Kind of a nice way to think about it that will make it easy for us, hopefully, to do in future problems. So I need to break x sine x. Let me use a new color. I need to break this stuff up into an f and a g prime dx. Okay, I'm going to do it in the simplest way imaginable, maybe. We're going to let f of x be the function x. And then g primed of x dx. Dx always goes with g prime. Is the remaining function. Let me clean that up. It's a little hard to read. I'll write it down below. So g primed of x dx. So is sine x dx. And so between the f, again, I'll go to red this time. Here's f. Here's g prime dx, and we've accounted for everything here. Here's our f. Here's our g prime dx, okay? And as soon as we make our decision, then we see on the right-hand side, we need to know f prime. Well, if f is x, then f primed is just 1. And if g primed is sine, then g of x is going to be an antiderivative of sine. Well, let's use minus cosine for that. We could add on any constant. What we're going to do is add our constant to the very end. We'll save it for then. And so now, putting the pieces together, we get that our integral, x sine x dx, is equal to fg. Here's f, here's g. So minus x cosine x. And then our formula has a minus sign. And here's the big trade-off. If we know this integral, we're in good shape. Well, f primed is 1. So that's nice and easy. And g is minus cosine x. And we know that. In fact, not only do we know it, it's easy. So the antiderivative we've been given, we can write it as minus x cosine x. Notice we have two minus signs, this one and that one. And the antiderivative of cosine is sine, so we'll just get plus sine x. And like I said before, here we'll add in the constant c. All right, so there it is. The antiderivative of that function is this one. And I'd encourage you to take the derivative of this function. I'm not going to do it, but take the derivative of this function and see if you don't get x sine x. You better. I'm confident you will. All right, like I said before, I'm going to develop a way to think about this that hopefully will allow us to be a little more efficient. So let me write the formula out in all of its detail. F of x, g primed of x, dx equals f of x, g of x, minus the integral of f primed of x, g of x. So here's what we're going to do. The strategy is as before. This is a different way to think about the pieces. I'm going to pick part of this function to be replaced with the variable u, and we're going to let it be just f of x. And then g primed of x dx, we're going to, okay, so that's a differential, so it needs to be equal to a differential. We're going to call dv. And then, if u is f of x, du, the differential, is f primed of x dx. And g of x, because we have g primed and we have the differential, it's just an antiderivative. Well, the antiderivative of dv is v. So then we take the right-hand part here. So let's write the whole thing. So on the left-hand side, I get the integral of u dv. All right. This is u. This is dv, you can see. equals, well, f times g is just u times v. So we'll say uv, I'll go back to black, minus the integral, and then we have, notice we have f prime of x dx, that's du, and then we have g, which is v, so v du. Okay, and that's the way we're going to think about it going forward. Okay, that's the way I'm going to write it. If the way we did it originally, this picture's getting a little bit cluttered, but let me circle in green. Here is actually what we're doing. If that makes more sense to you than this UV version, then use it. I'm going to use the UV version. All right, let's do another example. Go away. So we'll leave that at the top. Black. So let's do xe to the minus x dx. So a good indication, it's not, I mean, there are some exceptions, but when we have a function that's the product of two functions, and their derivatives are not related to each other. The derivative of x has nothing to do with e to the minus x. The derivative of e to the minus x has nothing to do with x. So a traditional substitution is probably not going to work. Then we should immediately start thinking by parts. And so I'm going to let u be the thing that has a nice, easy derivative. And we have to think ahead a little bit. What we put on dv, we need to know its antiderivative. So I could put either part there, x or e to the minus x. When we finish this, I'm going to show you what happens if we make a bad choice. But this will be a good choice. As soon as I make my substitution, then I calculate the related parts, the du and the v. The antiderivative of e to the minus x is minus e to the minus x. When we integrate, it cancels out the differential. So we just get v. And now we put the pieces back together. This thing is equal to uv, which is minus x e to the minus x, minus the integral of v, which is minus e to the minus x du. And du, of course, is just dx. If we clean that up a little bit, I get plus the integral e to the minus x. And again, just like the last example, we get a nice, easy trade-off integral. So minus x e to the minus x, and then another minus e to the minus x. Notice, to find this antiderivative, we already did it once in this problem right up there. We'll do it again, and we will add on a plus c, but let's rewrite the whole thing down here in nice, easy fashion. So what we have discovered is that the integral of x e to the minus x dx equals minus x e to the minus x minus e to the minus x plus c. And we can factor out a minus e to the minus x and get a prettier version, maybe. X plus 1 plus c. And again, I'd challenge you to take the derivative of that and see if you don't end up with x e to the minus x. And don't make a mistake when you're checking it. All right, I promised you I would show you what happened if we make a bad choice for our u and our dv. If we do it, it's going to happen. It doesn't mean the problem's not solvable. It just means we need to take a fresh start. We'll go back and reassign our u and our dv. So let's take a look at the last example. And I think after a while, pretty quickly, you'll get the idea that what I'm going to do here is not going to work. And then I'm going to do another example where it actually turns out pretty nice. But all right, so maybe I say, well, x has a really nice antiderivative. So my dv, I'm going to put the x over there. And that means the u is just e to the minus x. That's a nice derivative. We calculate the related parts, the derivative of e to the minus x minus e to the minus x dx. No problem there. But now we run into something, we can find this antiderivative, but hopefully you're not feeling really good about it. It's a more complicated function than the one we started with. Now, maybe that's not a fatal flaw. Let's put the pieces together and see what we get. So if we can do this, this antiderivative is going to be uv, which is 1/2 x squared e to the minus x, minus the integral of v du. Well, notice there is another minus. Actually, I'll just write it like this. V du is 1/2 x squared times minus e to the minus x dx, which is 1/2 x squared e to the minus x plus 1/2, cancel the minus, since I've got a plus minus here, minus there, gets us a plus. And this 1/2 comes out here. And then what's left over is x squared e to the minus x. And notice that's more complicated than the one we started with, which says probably made a mistake. Okay, so if we would have been serious, this was our first attempt, then we would abort it and we wouldn't get mad. We wouldn't think we wasted our time. We would just think we need to make another set of choices for how we're going to break down the parts of the function, the antiderivative we were given. Okay, and as promised, here's another example. Get this stuff out of the way. So let's take something like x cubed ln x dx. All right. So part of this we need to put on a piece of the by parts rule where we can take the derivative, and part of it we need to take the antiderivative. Well, if you look at this function, x cubed ln x, hopefully you'll recognize that we do not know the antiderivative of ln x. Well, we're actually going to work it out here shortly. So I can't put ln x all by itself on the dv. I could not find v if I did. So even though it feels sort of contrary based on the last example, which didn't work, what we're going to do, we can take the derivative of ln x, no problem. So we're going to put ln x on the u and the polynomial x cubed on the dv. And then we calculate the related parts. The derivative here is 1 over x. The antiderivative of x cubed is 1/4 x to the 4th. So we get by parts rule 1/4 x to the 4th ln x, u times v, minus, and then here's the big trade-off, v du, which is 1/4 x to the 4th, times du, which is 1 over x dx. And notice, miraculously, the ln has gone away. And if we clean that up, I can take the 1/4 out and cancel an x. Leaves me x cubed. And easy antiderivative there. 1/4 x to the 4th. So let's take out 1/4 x to the 4th just for the fun of it. I get ln x minus 1/4. And then we'll add a c on. And there it is. This guy's antiderivative is that guy. And what made this breakdown over here work is the fact that for the derivative of ln x, the log goes away. So the parts that the by parts needs, which is everything except u, the ln x goes away as far as the second integral is concerned. All right, another couple of examples. As I promised, We can actually use by parts to fill in some gaps. The first one is ln x dx. If you think about all the work we've done, it's sort of amazing that we have never yet stumbled onto the antiderivative of ln x. And the reason is we just have never seen a function whose derivative is ln x. And we can't do it by ordinary substitution. We can do it by parts. We'll do it like this. I have to put ln x on the u because if I put it on the dv, then in order to find v, I need to know this antiderivative. We don't know, it's what we're trying to find. So dv is going to get just the dx. So that u dv is all of the original function. And then I calculate the parts 1 over x dx for du, and v is just x. So we get uv, which is x ln x, minus the integral of v du, x times 1 over x dx, which is x ln x, minus the integral of 1, and that's just x. Let's factor in x out. Not necessary, but I'm going to do it. And then we'll add on our plus c. So the antiderivative of ln x, there it is. You can think of it either way. If you think of it this way, we can add a c in there. Okay, a similar problem. Inverse tangent. We do not know its antiderivative. We've never seen a function whose derivative is the inverse tangent. We know the derivative of the inverse tangent, but we've never seen a function whose derivative is the inverse tangent. I can solve it just like the last example. I have to put inverse tangent on my u because I don't know its antiderivative, and that means dv is just going to be another dx. So then the derivative is 1 over 1 plus x squared dx, and v again is just x. So by parts we get uv, which is x inverse tangent of x, minus the trade-off integral, v du, which is x times 1 over 1 plus x squared dx. So let's write like this. So this one's a little more complicated than the earlier ones, but we know it. We can find it by substitution. The derivative of the bottom, notice, is 1 plus x squared. The derivative of that is 2x, and I have the x here. All I need is to invent a 2, and of course cancel it out, so it's the same function. So what I'm doing here is letting u be 1 plus x squared, and du is 2x dx. And then that integral, there's a 1/2 out in front, but the integral part of it just becomes 1 over u du. Check it out yourself and make sure. And therefore, the antiderivative will be a log. The log of the bottom. Notice that the bottom can never be negative, so I don't need absolute value signs. Write a plus c, and there we have it. The antiderivative of the inverse tangent. That. So you probably never guess it in a million years, like what's the log doing inside there? But that's the way it turns out. I'd encourage you to take the derivative of this function and see if it doesn't all turn out to just be the inverse tangent. Might be sort of interesting. Let's try another example. So x squared e to the 2x dx. It's similar to one we did earlier. I'm going to let x squared be on my u, and dv is going to be e to the 2x dx. And then du is the derivative, 2x dx. V is the antiderivative, 1/2 e to the 2x. If you're not sure, check that out. Equals uv 1/2 x squared e to the 2x minus the integral of v du across here. Notice the 1/2s cancel, and I'm left with x. And this x survives, and then over here, e to the 2x. All right. This integral we do not know. So have we wasted our time? Well, not really. Notice that it's simpler than the one we started with. In fact, we were able to take this power and drive it down by 1. Do you suppose if we did integration by parts again applied to this integral, that we could drive that power down to 0 and therefore know the antiderivative? I think we can. So we're going to do integration by parts again. Don't forget this chunk here. He's going to just go along for the ride. And then for this green integral, I'm going to let u be x and dv be e to the 2x dx. Then du is dx. V is 1/2 e to the 2x, just like it was before. And so I get uv, which is 1/2 x e to the 2x minus the integral. The big trade-off is v du, which is 1/2 e to the 2x dx. Close paren. And now we know this antiderivative. We can just integrate it directly. So here's our answer. Maybe we'll write it in simplified form once we've worked it all out. So minus 1/2 x e to the 2x minus 1/4. Right? Because of this 2, we need to divide, multiply and divide by 2 again. And finally, let's factor out 1/2 e to the 2x, actually 1/4. Let's just factor out e to the 2x. And so I get 1/2 x squared minus 1/2 x minus 1/4. And now we'll add on a plus c. So notice we get this polynomial descending powers of x, all multiplied by e to the 2x. Okay, there's some other quirky things that can happen with integration by parts. I'll just assign problems and let you discover if there are any quirky things. So let's just summarize a little bit. I think we've done 3 fairly important things here. The first thing we've done is develop the integration by parts formula, uv minus the integral of v du. And hopefully through the examples you have a pretty good indication of what kind of functions this might work on. The second thing we've learned, second and third, is that we've solved some problems that maybe they weren't plaguing you, keeping you up at night, but we figured out the antiderivative of ln x. It's written in the scribbles up above. I'm not 100% sure I'm remembering it correctly, but I think we got that. Okay? And the third thing is we figured out the antiderivative of the inverse tangent of x. And I'm not sure I can remember all of it, so I'm just going to say C above. And the fact that I don't have them memorized means, you probably don't need to worry about that. If you are worried about it, you can write them on a 3x5 note card for our exam next week, next Wednesday. All right. That concludes the presentation of integration by parts. That we have lots we can learn by doing examples. I haven't mentioned it before. I think it was in the syllabus on the first day, but not since that. I've been trying to give you examples to look at, but there are probably an unlimited number on YouTube. Just If you want to know integration by parts or what did we do last week, volume problems or arc length, just go to YouTube and search, and you can probably find hundreds of worked out problems. And, pay attention, see how they do it. Hopefully they'll use a real similar notation. In the end, they have to do the same things we're doing. This is the way we solve these problems. So I'll give you some things to look at. There are things in the textbook, whether you're digital or hard copy, more examples worked out, and then on YouTube, lots of examples. And remember, my colleague at George Fox, the calculus professor on YouTube, has lots of problems as well. All right. Friday's class will be also presented via video, and I hope to be present on Monday as we talk about the exam. We kind of recap where we are, what we've done. It'll be good to do that together rather than via video. And then our exam will be on Wednesday, a week from tomorrow. Good luck, work hard.